The next step in our CFC procedure is to extract the phase of the low frequency signal and the amplitude envelope, or simply amplitude, of the high frequency signal. Let's try to gain some intuition for this operation by considering the amplitude and phase for an example signal. To start, let's look at the phase of the low frequency signal. What we see here is that as time progresses, the phase increases almost linearly from minus pi to pi. Then, at pi, the phase jumps suddenly to minus pi. What's the cause of this apparent discontinuity? Well, it turns out it's imposed by the space on which the phase evolves, which is a circle. As another example of such a space, consider the time on a 24-hour clock changing suddenly from 23:59 to 0000. In this case, the measurement has suddenly shifted discontinuously, but time has not. This discontinuity appears because we choose to measure time in a 24-hour interval. The same is true of the phase that we choose to measure from minus pi to pi. The two endpoints, minus pi and pi, actually touch on the space of a circle, but appear to discontinuously jump when we plot the phase versus time. Let's now look at the amplitude envelope of the high frequency signal. We see that the amplitude envelope outlines the extent of the deviations of the high frequency signal. Notice that the amplitude envelope fluctuates much less rapidly than the underlying high frequency signal. Okay, so to compute CFC, we now want to compare the two signals we've extracted from the data, the phase of the low frequency activity and the amplitude envelope of the high frequency activity. Now, a very reasonable question, how do we actually extract the phase and amplitude signals from the data? There are a couple of different ways we could do this, and here we're going to employ one of them by computing the analytic signal, which allows us to estimate the instantaneous phase and amplitude envelope of the LFP. We'll talk more about the analytic signal in the next video.